Now that we have a better understanding of fiber optics, connectors, and some of the ways network performance can be degraded, what tests and measurements can be made to verify performance and find sources of trouble? The most common tests performed on fiber networks are loss measurements using a light source and power meter, and fiber span analysis using an optical time domain reflectometer, or OTDR. However, actual test methods and equipment used will depend on the application, such as acceptance testing, quality assurance, and documentation or troubleshooting and restoration. The light source and power meter is used to measure attenuation by directly measuring the amount of light passing through a fiber under test and can provide very accurate attenuation readings. Optical loss testing often requires two people, one at the launch end and the other at the receive end of the fiber. The primary function of the optical loss test is to verify end-to-end attenuation of the fiber optic link, including the fiber, connectors, splices, and passive components. In addition, the power meter can be used for simple continuity checks. Light sources and power meters are the essential go-no-go instruments for fiber optics testing. Optical loss testing must be performed when a fiber system is first installed to verify fiber continuity, validate correct polarity, and certify that the attenuation of each fiber meets design specifications. Testing is then performed periodically as the system ages or is modified to verify that attenuation stays within tolerance. It is important that all tests be fully documented so that future tests can be quickly compared to previous values. Any increases in attenuation over time may be a sign of trouble that should be addressed before it causes a system failure. Unfortunately, optical loss testing can tell us nothing about reflections present in the system. The insertion loss and reflection meter is an ideal instrument for measuring the insertion loss in a fiber span bidirectionally, as well as the reflectance of the terminations. Although it does measure the magnitude of reflections, it does not provide information as to the cause of the reflections. The optical time domain reflectometer is an instrument used to test the light transmission ability of an optical fiber cable or span and is the only instrument that can determine both the location and magnitude of a problem. It can determine the length of a fiber, distance to events, total end-to-end loss, as well as the attenuation and reflectivity of discrete components along the fiber. OTDR measurements can be made quickly by one person and can provide details on the condition of all splices, connectors, and the fiber of a particular span. Its greatest strength is the ability to zero in on individual events along the span and provide attenuation and reflectivity information for the event. Although the OTDR is able to measure the reflectance of all the connectors in a fiber span, it is unable to determine the cause of excessive reflectance in these connectors. Other useful instruments for fiber optic testing include fiber identifiers and visual tracers. The fiber identifier is a handheld instrument that determines if a fiber is currently carrying an optical signal and in which direction the signal is traveling. The fiber identifier is often used when performing mid-entries into multi-fiber cables where specific fibers must be accessed, providing assurance to network users and the technician that only the correct fibers will be cut. Another handy tool for fiber technicians is the visual tracer. Using a visual semiconductor laser operating between 630 and 700 nanometers, it provides a quick and simple method of fiber fault location. When the red laser light is launched into a fiber, bad splices, fiber breaks, and bends glow brightly due to light leakage present at the fault. A common application for the visual tracer is troubleshooting connectors and jumpers. In this example, we can see the fiber is broken inside the connector ferrule, a fault difficult to isolate by other test methods. If the glow is apparent on the tip of the ferrule, the cause could be either surface damage, an internal break, or even contamination on the ferrule surface. In high-speed or mission-critical fiber systems, it is vital to verify the condition of connectors. How clean are they? Are they scratched or damaged in any way? It's been estimated that more than 70% of the problems found in optical connectors can be traced to dirt and contamination. In addition, because many contaminants are abrasive, mating dirty connectors can result in permanent damage to the precision optical surfaces of the termini, requiring repolishing or replacement. Handheld optical microscopes allow the technician to closely view the connector ferrule. Scopes are most commonly available with 200 or 400 power magnifications. The 200 power scope can show sufficient detail when inspecting multi-mode connectors. However, when testing single-mode connectors, the use of scopes with 400 power or greater is recommended. There are also a number of video-based inspection scopes available. These scopes can be safer to use than their optical counterparts. Because the operator is looking at an LCD screen and not the fiber itself, there is no chance for a stray laser beam to enter the eye if the fiber system is live. When examining connectors, look for scratches, pits, or cracks on the ferrule end. If you see any of these defects, especially over the fiber core, the connector must be repolished or replaced. Dirt, residue, and other contaminants should be easy to see. With the high magnification of the inspection scope, dust particles will appear as boulders on the ferrule surface, while oily contamination will usually appear as smears or blobs. All connectors in the fiber system should be checked with the inspection scope prior to each mating. This includes the connectors on circuit cards as well. Never assume that because the product is new, the connectors will be clean and free of damage or defects. The testing methods we have presented can identify many types of system problems, but they fall short in the detailed analysis of what may become the weakest link in the optical chain, the connectors. The ideal instrument for analyzing end-face quality is one that can provide a precise three-dimensional map of the surface of a connector's ferrule or termini using a non-contact measurement method. The instrument must also be compact and easy to use. The interferometer is just such an instrument.